I'm just going to take a couple minutes to go over some of the problems from the Chapter 7 test review. This review was in the textbook, so here are the pages. So I may not do all of them, but I'll do at least one or two in each section so you got a gist of what's going on. All right, so the first couple ask to determine whether each function is an exponential growth or decay. So we talked about exponential functions as being in the form of a times b to the x. Okay, when asked about growth or decay, you're going to use the b. So if b, or the number with the exponent, is greater than 1, then we have a growth. If it is less than 1, or in between 0 and 1 fraction, decimal, then it's going to be a decay. So if you look, the first one, number 7, is 4 to the x, so we have a growth. Okay, the next one, 0.25, that is less than 1, so we have a decay. Okay, 11 is 10 to the x, which is greater than 1, so we have another growth. And then lastly, we have 1/4, which again is a fraction, so we have a decay. Okay, the second part of the question asks to find the y-intercept. Okay, the y-intercept is always, if it was an ordered pair, 0, some y value. Okay, and the number in front always gives us the y-intercept. So for number 7, the y-intercept is 2, or if they wrote it as an ordered pair, the 0.02. Okay, the next one, number 9, is 3, or again, as an ordered pair, it would be 0, 3. Okay, the next one, even though it's a small number, it would be 0.0015. And then lastly, the number in front is 0.5, so we would use 0.5. And the only thing that sometimes might throw you off, let's just pretend for just a second, if all we saw was a 3 to the x, and there's no number in front, you can pretend that there's a 1 times 3 to the x. So in that case, since 3 is bigger than 1, we would still have a growth. But the y-intercept for a problem like that would be 0, 1, because 1 is like the number in front, even though you technically couldn't see it like the other ones. Okay, so the next couple say write a function for each situation, then find the value of each function after 5 years, round to the nearest dollar. So I will do the setup for both of them, but I'm only going to plug into the calculator for one of them. So again, when it comes to writing these exponential, we have some a times b to the x. And a always stands for the starting amount. Okay, the starting or initial amount. The b is always either going to be the growth or the decay factor. So when we look at these, I'm going to start with number 14. It says a 12,500 car depreciates 9% each year. Depreciates means that the value decreases. Okay, so we have a decay. So number 14, we need to find the decay factor. Okay, the decay factor again is my b. The decay factor, you're going to take 1 minus the percent decrease. Well, it says it's going to decrease at 9%. Well, 9% as a decimal is 0.09. Okay, if you take 9 and you move the decimal 2 places, you have 0.09. So if I take 1 minus 0.09, I get 0.91. So when it comes to writing my equation, I have some a times 0.91 to the x. So then we need the starting value. Well, the starting value for number 14 is 12,500. So my equation is 12,500 times 0.91 to the x. Okay, the second part of this asks us to find out what is the value after 5 years. So I'm going to take this and I'm going to plug in 5. So I have 12,500 times 0.91 to the 5th power. We're going to put this in our calculator and we're going to do the exponents first. Okay, so let me get my calculator. Okay, so I'm going to take 0.91 and I'm going to raise it to the 5th power. And when I do that, I'm not going to write all the decimals, but you get a 0.624 ... Okay, you're going to hold that number in your calculator, and then you're going to multiply it by 12,500. And you get a final answer of 7,800. If it says round to the nearest dollar, it's a 0.4. So we're just going to leave it at 7,800. Okay, so then we can plug in 5 into my equation and we're good. Okay, 15, again, I'm going to get the setup and let you do the calculator part. So it's the same gist about a baseball card, but this time the value increases. So for 15, we have a growth factor. Okay, so for the growth factor, you're going to take 1 plus the percent increase. Well, again, 3% as a decimal is 0.03. So my B is 1.03. So I get a y equals, okay, I have 1.03 to the x. And then I need my A, which is my starting amount. So the baseball card started at $50. Okay, so my equation is 50 times 1.03 to the x power. And then again, you would plug in 5 and you would get a value. All right, so the next couple ask you to determine how the equation compares to the parent function. Okay, so first thing I notice on number 16 is there's a 5 out in front. Okay, the times 5 tells me that this is going to stretch. I then have a plus 1 in with the x. Okay, up with the x tells me it's going to go left or right, and it always does the opposite. So it's going to go to the left one. And then the plus 3 on the outside tells me that this is going to go up 3. Okay, so before it does not ask you to graph it, but I'm going to go ahead and review what the graphs of exponential functions look like. Okay, they're multiple choice, so we just need to kind of know the basic shape. So the first thing that I know about these exponential functions is that it's 2 to the x, which tells me that we have a growth function. A growth function tells me that as I go left to right, the function is going to grow. Exponential functions, also have an asymptote of the x-axis. Okay, so we're taking this exponential function and we are shifting it to the left one and up 3. So I'm going to go ahead, I guess I can get my highlighter, and I'm going to highlight the asymptote. Again, instead of the x-axis, we're going to go up 3, and we have a new asymptote, or the line that the graph is going to approach. Okay, from there, normally we start at 5, right? That's my starting value, 5. So I'm going to take that starting value and I'm going to shift it to the left. From there, we just need to know the basic shape. So I know exponential function growth is going to get taller and taller and taller. Okay, so it's going to look something like this. It's that skateboard ramp that is increasing as we move left to right. Shift it up and to the left. Okay, so we're going to look at the other one over here. This time it's to the 1/3, so we have a growth function. Or sorry, excuse me. We have a decay function. Okay, to the 1/3 fraction says that we have a decay. A decay functions, instead of going and getting increasing as we move left to right, they're going to start tall and they are going to go towards 0 as they move left to right. Okay, so when it comes to the transformations, I have a negative here, and the negative tells me it is going to reflect. The 2 tells me it is going to stretch. And the -2 up with the x tells me it's going to move to the right 2. Okay, so the reflection, I'll go ahead and do my asymptote. So it's not moving left to right. So I know my asymptote is still going to be the x-axis. Okay, we said usually these decay functions are going to come and approach 0 this way. However, since we're reflecting it, we're going to take that and we're going to approach from the other direction. And we also said it's going to move right, so I'm going to come over to. And again, this is a multiple choice, so I just want you to get the gist. So it's going to then get farther and farther and farther away this way. And as it moves left to right, it is going to approach 0. It's just going to approach from the negative direction because it said we are going to reflect. All right, so the next couple say find the amount in a continuously, that's a big word there, continuously compounded account that gives the following conditions. We said in our notes, I think 7.1 or 7.2, we talked about continuously compounded interest. The formula that we used is A of t equals P. Since continuously has an E, we're going to use times E to the RT. So I'm going to do one of these and then you can try the other one. So I will look at number 19. So P is the principal. So I'm going to go ahead and say, okay, well, instead of P, I'm going to put 250. E is a number. Okay, so I'm going to go ahead and put E. R is the rate. So we have 6.2, but we use the rate as a decimal. So if I move the decimal 2 places, that is 0.062. Then the time in years is 2.5. So I'm going to go ahead and multiply RT. Okay, so if I multiply 0.062 times 2.5, I get 0.155. So that's why I'm going to come put here, R times T, 0.155. This now becomes calculator. So just like the last one, I first want to do the exponents. So I'm going to take E to the 0.155, and you get like a 1.167 number. I want you to hold it in your calculator. Okay, you're then going to take that number and multiply it by 250. And it says then find the amount. We're going to put $291.91. Okay, the amount in a continuously compounded account. If it asked you ever how much it increased, then you would take this 250 and subtract 291, and it would tell us that the amount that we grew was like $41.91. But how much is in the account? $291. Okay, this evaluate the expression. These are all calculator. Okay, so what I'm doing here, if I'm doing e to the negative 3, so we all have an e button, which you have to do second and then natural log, and that makes e. And then you'll do the exponent caret button, and then you'll do the negative 3, and then you hit enter. Okay, that's like the pink calculator. So the other kind, you have to do the opposite order. So you'll do the negative first, okay, the 3, and then you'll hit second natural log, or if you have an E button, and then you can hit enter, or it's going to appear the number. Okay, so those are the two different types of calculators. So on mine, okay, I'm going to hit negative 3. Okay, and I have an E button, so then I hit the E, and I end up getting 0.0498. Okay, same type of thing. Okay, I'll do one more just so you can check. E to the 5th is going to be 148.413. Okay, so the book has the answers to 21 and 23 if you want to go try them. But again, these problems here are all calculator problems. All right, write each equation in logarithmic form. So we're going to write these as logs. Before I do, okay, we said log base b of a, okay, equal to x can be rewritten. The base comes up, the exponent comes over, so x becomes the exponent, okay, equals a, and this number here just kind of stays, is our conversion factor. So if I want to write this as a logarithm, I'm going to start 25 here by writing the word log. The base of the exponent is 2, so I'm going to write log base 2. I'm going to put my equals, and it's always equal to the exponent. So all I have to do to finish this is just fill the 0.125, and I'm done. Okay, so 27. Again, I have log base 10 equal to negative 3. And then 0.001 just fills. Now this one is a special one because log base 10 you don't actually write. This is called the common log. So my final answer is just log of 0.001 equal to negative 3. Because it's the common log, you can just go ahead and drop the 10. And evaluate each logarithm. So again, 29. I'm going to write log base 3 of 1/9, and in my mind equals x. So here's what this is saying. We convert it back to an exponential. 3 to what power is equal to 1/9? Okay, so here's what I'm going to do, because y'all don't a lot of times like these fractions. I'm going to pretend over here that this problem was 3 to the x equals 9. And the way we evaluate this is we try to get the same base. So 9 is 3 times 3, which is 3 to the second. So 3 to the x equals 3 to the second, and we would get 2. Okay, however, we don't want 9, we want 1/9. And the way we turn numbers into fractions is to make the exponents negative. So if I make this 3 to the negative second, it becomes a fraction. So what I have here is 3 to the x equals 3 to the negative second. So log base 3 of 1/9 is negative 2. Okay, 31 was the other one. Same thing in your mind, you're going to put equals x, and you're going to rewrite it. So 2 to the x equals 1. And this one's kind of tricky because you can't make them have the same base. So if we just kind of think about it, any number, some power, will give us 1, and that number is 0. So 2 to the 0 power equals 1, so log base 2 of 1 is equal to 0. Okay, just to do one more, I know it's not on the review, but this one here, you imagine there's an equals x. It's saying like 2 to the x equals 64. So 2 to what power equals 64? If I take 64 and I break it down into 2 times 32, 32 is 4 times 8, and we have 2 times 2, and 8 is 2 times 4, which is 2 times 2. There are 1, 2, 3, 4, 5, 6 2's here. So 2 to the 6th power, so 6 would be my answer. A graph each logarithmic function. So again, the difference between logs and exponential functions, or the big difference, is the asymptote. So where exponential functions, we said the x-axis was the asymptote, this logarithmic function, the y-axis is going to be the asymptote. And the way that we said to graph them is we're going to use what we know about exponents. So here the base is 3. So I'm going to make this 2 3-point t-chart of 3 to the x. I'm going to use exponentials. So I'm going to plug in -1, 0, and 1. Okay, 3 to the negative first power, if you put it in a calculator, is 0.33. 3 to the 0, or any number to the 0, is 1. And then 3 to the first is 3. However, we're not graphing exponential functions, we're graphing logarithmic functions. So we've got to know exponentials and logs are inverses. So we're going to take these points and we are going to flip them. So this becomes 0.33, -1, 1, 0, 3, 1. And these are the points that we are going to use on the graph. So if I go over 1/3, down 1, okay, put a dot. Over 1, up 0, second dot. Over 3, up 1, third dot. Okay, I know that as we go this way, it's going to approach the y-axis. So then I can just continue the shape out in the other direction. Okay, so same type of thing on this next one, but here we have a +2, which tells me it's going to go up 2. Okay, the base, if you don't see one, there's like a 10. So we're going to graph or use 10 to the x. So again, if I plug in -1, 0, and 1, I end up getting 0.1, 1, and 10. And we're going to take those points again and we're going to flip them. And we said it's not moving left or right, so I still have this asymptote of the axis. Okay, so I'm going to graph, okay, here, here, over 10, up 1. However, this time we have this +2. The +2 is going to take this function and move it up 2. So I'm going to take all these points and I'm going to shift them up 2. So the green is my final answer. Okay, the green is the one that took this logarithmic function and shifted it up 2. Okay, so this time I'm going to do a little bit more of a rough sketch. The 3 tells me it's going to stretch. Okay, the 2 says I'm going to use 2 to the x. So if I plug in -1, well, so I have x values, and I have my y equals 2 to the x. So negative 1 gives me 0.5. 0 gives me 1. 1 gives me 2. I haven't again moved left to right, so I have my asymptote still of the x-axis. We said since we're not graphing the exponential functions, we are going to take these points and flip them. So we have 0.5, negative 1, 1, 0, 2, 1. But since we're stretching all these y values, we're going to multiply by 3, okay, all of the y values. So what this becomes is 0.5, negative 3. Okay, 1, 0, and then lastly 2, 3. So negative 1/2 down 3. I still 1, 0. And then 2, 3. And again, it's going to approach. This time it's just a little bit taller. Okay, so last one here, I'm just going to do the short version. The biggest thing you've got to be able to determine are the transformations. So this time there's a +1 on the inside, which tells me this is going to go to the left one. So I'm going to take my asymptote, which is usually the y-axis, and I'm going to shift it left one. Hey, it is base of 5. However, if you can at least just get that it's to the left, then you know that it's approaching the y-axis. You should have a decent sketch. Again, note that this is pushed to the left one, even though it's kind of hard to see because I can't draw a straight line. All right, so now we're just doing transformation. So anytime we have a number in front, it's either going to be a stretch or compress. Since it's greater than 1, we have a stretch. A +1 on the inside tells me this is going to go to the left one. 37, there's a negative. The negative tells me it is going to reflect. And the +2 on the outside tells me it is going to go up 2. Okay, these next couple ask us to write them as a single log. So again, here's my kind of review. You have log base b of a plus log base b of c. It becomes log base b of a times c. So you can merge addition through multiplication. Okay, similarly, if you have log base b of a minus log base b of c, okay, it becomes log base b of a divided by c. I didn't really leave enough room, so the last one here, I'll draw another one, is if we have log base b of a to the c power. That exponent comes out in front, and it becomes c log base b of a. Okay, so these are my 3 rules for logs that you've got to be familiar with. So when we look at 39, 39 has log base b, log base 2. I'm going to write log base 2. And there's a subtraction. Well, to merge subtraction, we are going to divide. This becomes log base 2 of 5 divided by 3. And I'm okay if you just leave it like that. Okay, so the next one, again, is subtraction. So we have log of x minus y. And the subtraction tells me if I merge these, I can divide. So I'm done with that one. Okay, the last one here has a couple of things. The first thing, these numbers on the outside can go inside and they become exponents. The last thing we have here is a plus, and to merge addition, we said we are going to multiply. So it becomes log base 4 of x to the third times x to the second. And if you want to go ahead and combine this, this becomes log base 4, add the exponents of x to the fifth. Okay, so now we're going to do the same type of thing, but we're going to go backwards. So I'm going to start here. I have a log and a 4. I have a log and an s. I have a log and a t. So when we look at this, we said, okay, we're multiplying. And we said to split multiplication, we're going to use a addition sign. The last thing we have to do here is deal with the 4, and we say exponents can come out in front of the log. So I'm going to put a 4 out in front of the s, and I am done with 45. Okay, 47. We have a log of x plus 3. So all we can do here is take the 2 and put it out in front, because we can't split addition inside. If it was multiplication, we could split it. Otherwise, we've got to leave it alone. Okay, 49. We have a log and z and a log 5. The first thing I noticed this time, it's division, and we split division with subtraction. And then the last thing we have is this 2 here, and we say the exponents come out in front. This becomes 2 log z minus log 5. All right, I'm going to do one more just to kind of reiterate and practice. I'll go ahead and do 44. Okay, 44, we have a log base 4 of x, and we have a log base 4 of y. But this time they're being multiplied, and we split multiplication with addition. Okay, the exponent 2 comes out in front, so the 2 comes in front of the x, and the 3 comes in front of the y. All right, change of base formula. The change of base formula says you have log of base b of a. You can rewrite it as log base c of a divided by log base c of b. Okay, for the purpose of these, we are either going to use ln or we're going to use log, because both of those we can put in a calculator. Okay, so 51, this is going to become log of 10 divided by the log of 3. So again, this now becomes calculator practice. When I type this in, you may need parentheses. Okay, divided by parentheses. So I'm going to do it in my calculator just so I can get an answer. And then we'll see if y'all can get this. So like 10 log divided by parentheses 3 log, close parentheses, hit enter, and I get approximately, let's write that, 2 0.096. So now we're to the last little bit, solving. Okay, so I'll do a couple of these. Just kind of a reminder, we use logs or natural logs to solve exponentials, and we use exponentials to solve logs. Okay, so first thing we're going to do, I'll do 55. We have 5 to the x plus 3 is equal to 12. First thing we're going to do is isolate, so I'm going to subtract 3 from both sides. So 5 to the x is now equal to 9. Okay, we're then going to take the log or natural log of both sides. And when we do that, the exponents we can write out in front. So we have x times the natural log of 5 is equal to the natural log of 9. And the final step is we divide by 5, or natural log of 5, excuse me. Okay, and then again, this becomes calculator. So you can't just divide 9 by 5, you have to make sure you put the natural log. Okay, or you could do it with log LOG. Okay, so I'm going to do 9 natural log divided by parentheses natural log 5, close my parentheses, hit enter, and I get 1.36. We're going to write it as an exponent. So when we do that, the base, which is the 2, comes up, the 5, which is the exponent, comes over, and it's always equal to what's left, 4x. So my calculator, I'm going to take 2 to the 5th, and 2 to the 5th gives me 32. So 32 equals 4x, and I divide by 4. So x is equal to 8. Okay, solve each equation again. Check your answer. So I have an e to the 3x equals 12. We said exponential functions, I like to take the natural log of both sides. So I'm going to take the natural log of e to the 3x and set that equal to the natural log of 12. And again, like the last one, you can take the 3x and you can put it on the outside. However, we talked in class about how ln and e can do each other. So those essentially cancel, so I'm left with 3x is equal to the natural log of 12. And I can divide by 3, so x is equal to, again, this becomes calculator. So I have the natural log of 12, and then divided by 3. And I get 0.828. All right, so let's look at one more of these. Okay, 67. This time we have to start by writing as a single log. So we're going to merge what we did earlier with what we're about to do. So I'm going to take this 2 on the outside, and it's going to go to the exponent. I'm going to take this 3. It's going to go to the 2, and then the plus tells me I'm going to merge these through multiplication. This becomes the natural log of x to the second times 2 to the third equals 5. Well, 2 to the third is really just 8. So we have the natural log of 8 x to the second equals 5. Okay, since we started as an exponent, if you need to remember, ln is log with the base of e. So when we rewrite this, this is e to the 5th equals 8 x to the second. So the e comes up, the 5 comes over, equals 8x to the second. So now we can solve. So I'm going to divide by 8. Okay, so then I'm going to put this in my calculator. I have e to the 5th divided by 8. And that is like an 18.5 number. So then I'm going to take the square root of both sides. So x is equal to 4.307. All right, so we got a couple more. Let's look at 68. Again, I'm going to write it as a single log. So I'm going to write this as the natural log of 4. The subtraction says divided by x equal to 2. Again, natural log has a base of e. This is e. The 2 comes over to the second equals 4 over x. It might help us if we think about this as a fraction into a fraction. We're going to cross multiply. So this is x times e to the second equals 4 times 1. And then I can divide by e to the second. And again, once I get that, it's my final answer. So this now again becomes calculator. So I have 4 divided by e to the second. And that gives me 0.541 if I put it in there. All right, so 69 is 4e to the x minus 1 equals 64. So again, we're going back to an exponential function. We're going to use logs. First step, I'm going to divide by 4 and isolate. So this becomes e to the x minus 1 is equal to 64 divided by 4, which is 16. Okay, we're then going to take the natural log of both sides. Okay, ln of e is going to undo each other or undo itself. So I've got x minus 1 is equal to the natural log of 16. And the final step here is to add 1. Note this does not become the natural log of 17. So to find x, I'm going to take the natural log of 16, get an answer, and add 1 to it. So again, 16 natural log 2.77 plus 1. So my final answer is 3.773. All right. So the last one that I will do here is 71. I just wanted to set up the problem and solve it. So it says initial investment of 3.50 is worth $429 after 6 years of continuous compounding. Okay, continuously says if we're going to go back to our formula, A of t plus P times E with RT. Okay, it says find the annual interest rate. So we're going to start to plug in what we know. So the first thing we know is we started with 350. So the P, the principal, is 350. So we know after 6 years, it's worth $429. So it's equal to $429.29. I know I'm going to have an E. The rate is what I'm trying to find. And I know that the time is 6 years. So R times 6. Okay, once I get all the pieces in the setup, it's a solving problem. So we're going to isolate. So the first thing I'm going to do is divide by 350. So I'm going to take 429.29 divide by 350. And I get 1.2265, blah, blah, blah. Okay, so that equals E, 6 times R to the 6R. From here, we are going to, again, solve. We're going to take the natural log of both sides. And E, so the natural log is going to do itself. So we have the natural log of that 1.22 number equal to 6R. So the final step is to divide by 6. So I'm going to take the natural log, divide by 6, and you get R is equal to 0.03. And if it says, well, 0.34, and if it says find the interest rate, we're going to take that and we're going to move the decimal 2 places. So the interest rate is 3.4%.